Section 4.6 gives us a chance to look at area in a different setting. So we're going to call this area under curves. My first example goes like this. Jeff entered a race. He has an app on his phone that logs his velocity. The graph above represents his velocity during the bike race. The graph is here. There's like a horizontal segment, and then it goes here, and then the graph is here. So those are the pieces of the graph. The x-axis is labeled with a half, 1, 1.5, 2, 2.5, 3, and the units is hours on the x-axis. The y-axis is labeled with 10, 20, 30, 40, 50, 60, 70, 80 miles per hour. The unit is miles per hour, so that's a velocity. As time goes by, you can tell what his velocity is at different times during the race. This was a 3-hour race, a half hour and 1 hour. You know he's going 20 miles an hour. Then he goes faster during hour 1 to hour 2. He's going 30 miles an hour between hours 1 and 2. And then he's going back down to 20 miles an hour in the last hour of the race. Okay, we're going to look at this a little closer. Number 1, what are the units of the output? So the output is the y value, and it's represented on the y-axis. So those units are miles per hour. Number 2, what are the units of the input? The input would be the x-axis in this graph representation. So the units there are hours. Number 3 asks us to do an interesting maneuver. It says to multiply those units together. So multiply the units of output and the units of input against each other. The output was miles per hour times hours. And you know your algebra, if you're going to multiply by hour and hours in the denominator, then the hours are going to cancel and you're just left with miles. This is what we get when we multiply the units together. We get miles. So what we're going to do is we're going to find area under the curve. And as you know, when you find area of a rectangle, okay, the first one's going to be from t equals 0 to t equals 1. I'm going to actually outline that. This region is in the shape of a rectangle, and you know that the formula for area of a rectangle is base times height. We're going to be multiplying the units along the bottom, the x-axis, times the units going vertical. So those are the y-axis units. So when we multiply the units together, we're going to have the hours cancel when that happened. So I'm going to write that down as well. The base of that rectangle is 1, and the unit is hours. So I'm going to write 1 hour. Multiply that times the height of the rectangle, which is 20, and put the units there. So 20 miles per hour. The hours unit cancels, and we're left with miles. 1 times 20 is 20 miles. So we're saying that the area under the graph from 0 to 1 represents something. It represents 20 miles. Number 5 asks us to say what it represents. If Jeff is riding his bike for an hour and he's going 20 miles an hour, how far has he actually traveled? Well, obviously he's traveled 20 miles if he's traveling 20 miles an hour the entire time. So this tells us that Jeff has traveled 20 miles in the first hour. You can tell that the math problem itself, finding the area of the rectangle, is very easy. It is something that we can do. But this concept of finding area under the curve on a graph, as we have done here, is more of a calculus idea. So we're showing you that this calculus idea of finding area under the curve is something that we could do right now at the geometry level, and we don't know everything about calculus yet, but that is a talent we're going to need to have when we get to calculus. So it is definitely something within your reach. And so we're going to go along and practice this a little more. Hopefully you enjoy this first example. The area under the curves are all going to be rectangles, so it's going to be quite nice. The next question asks us about the area from t equals 0 to t equals 2. Now we already found out the answer from t equals 0 to t equals 1. So I'm going to write that answer down, 20 miles, and then I'll simply add on the area for the rectangle between t equals 1 and t equals 2. So in the picture, from t equals 1 to t equals 2, we have a base of 1 and we have a height of 30. So all I have to do is include the units when I do that. A base of 1 hour and a height of 30 miles per hour. So write that down. 1 hour times 30 miles per hour. And now you know when we multiply the numbers together, we get 30. But when we multiply the units together, we're going to cancel hours on the top with hours on the bottom. So our answer will be 50 miles. This answer represents the distance that Jeff has traveled in the first 2 hours. And then number 8 is asking how far he traveled during the entire race. We know that from t equals 0 to t equals 2, he traveled 50 miles. We can write 50 miles down, and then we're going to add on the distance traveled from t equals 2 to t equals 3. Looking back at that picture, t equals 2 to t equals 3 means the base of the rectangle is 1, and then the height is 20. So we're going to find the area of a rectangle with a base of 1 and a height of 20, but we have to include the units. The base is 1 hour and the height is 20 miles per hour. Cancel hours because we have an hour on the top times an hour on the bottom, and add those together. The result is 70 miles. Looking at problems 9 to 14, we have a different picture. In the graph, the output units are labeling the y-axis. So the output is meters per second. I'm going to write it like I would in algebra class with meters over the word second. So it forms a fraction. And when I do multiplying, I can do canceling with the units. Number 10, the units of input are labeling the x-axis, and that is seconds. Number 11, when you multiply the units of output times the units of input, what do you get? And that is meters over second times seconds. So we have a second on the bottom, we have seconds on the top, and those will cancel when we multiply. So we're left with meters. So in this picture, the area under the curve is going to represent meters, which is like a distance that somebody has traveled or something has traveled. Let's begin with number 12, looking at the area under the curve from 0 to 4. From 0 to 4, we're going to have a triangle. So I'm going to draw in a vertical segment here at t equals 4, and that creates a right triangle, and I'll need the formula for area of a right triangle. I'll use 1/2 base times height. 1/2 times the base. The base is 4 units long and the units are seconds. So I'll write 4 seconds. The height of the triangle goes all the way up to 20 and the units are meters per second. So let's write that as a fraction. 20 meters per second. Now you can see the seconds unit will cancel when you multiply. But I also have more numbers here. 1/2 times 4, or 2 cancels with 4 and leaves a 2 behind. So I will get 40 from multiplying, and the units will be meters. So that means between time t equals 0 to t equals 4, the object has traveled 40 meters. Number 13, I need to find the area under the curve from t equals 0 to t equals 16. And I already have a number from 0 to 4. I'll start with the 40 meters and add on the area from t equals 4 to t equals 16. I'm going to draw a vertical segment at t equals 16. That creates a rectangle in the middle here. So I'm going to do area as base times height. The rectangle goes from 4 to 16, so it has a base of 12. The base is 12 seconds. Put the unit there, and then the height is 20, and we're going to write the units as meters per second. 20 meters per second. The seconds will cancel. I will have to do 12 times 20, which is 240. So 240 and 40 is 280, and the unit is meters. The object has traveled much further in that time. So the greater the area, the further the distance. Last one, going from t equals 0 to t equals 24, I can take our 280 meters from the previous section and add on the area. The area of this last region is a triangle, so I'm going to set up 1/2 base times height. The base goes from 16 to 24, so that's a difference of 8. The units horizontally are seconds, so write 8 seconds. And then the height, you know, again, is 20 meters per second. Seconds unit is going to cancel, and I can cancel the 2 and the 1/2 with 8. So cancel the 2 with 8, and that leaves a 4 behind. So I'm going to do 4 times 20 for 80, and add that to 280. I'm getting 360 meters. We have one more example because there's another situation that can happen. Notice how this graph dips below the x-axis. When the graph dips below the x-axis, the region that is created between the x-axis and the graph is now below the x-axis. So when we calculate the area of that region, we denote it as a negative area. So when the area is above the x-axis, it's positive area. When the area is below the x-axis, it's negative area. Number 15, what are the units for area under the curve? Whether the curve we're talking about is over here, or the one below, or we're going to have another part right over here in the shape of a triangle. Let us see our units. The output units are feet per second squared. So that's an acceleration. That's not a velocity this time. Multiply that times seconds, and one of the seconds on the bottom is going to cancel with this second on the top. So the output is feet per second. The result is units of feet per second for area. This time, in this example, area under the curve represents a velocity. Area under the curve from t equals 0 to t equals 6. That shape that we have from t equals 0 to t equals 6 is a trapezoid. So this horizontal base and this top base, they're parallel to each other. So I can use my area of a trapezoid formula. Area of a trapezoid is 1/2 of the height, or h over 2, times the sum of the bases. I'm going to take the h off the top of the 1/2 for this. I'm going to get 1/2. The height of the trapezoid is 15. The units are feet per second squared. The bottom base goes from 0 to 6, so that is 6 seconds. Add that to the upper base, which goes from 0 to 2, so that's 2 seconds. Therefore, I'm looking at 1/2 times 15 feet per second squared times 8 seconds. The seconds unit is going to cancel with one of them on the bottom, and 1/2, the 2 on the bottom of 1/2, 2 cancels with 8 and leaves 4. I need to do 15 times 4, which is 60, and the units are feet per second. 60 feet per second is the answer. Number 17, the area under the curve from t equals 6 to t equals 16. That is also a trapezoid. However, this time, that region is below the x-axis. So in the end, we're going to write our answer as a negative answer. And I'll show you how I would set this up. So the formula for area of a trapezoid, 1/2, the height of this trapezoid below the x-axis, it goes down to negative 15. I'm going to use that negative to help me remember that my answer needs to be negative in the end. And the units for that height are feet per second squared. The bases, okay, the lower base goes from 10 to 14, so that's a length of 4, so that's 4 seconds. And add that to the upper base, which goes from 6 to 16. So that's a length of 10 in there. So that's 10 seconds. It's 1/2 times negative 15 feet per second squared times 14 seconds. The unit of seconds is going to cancel with one of them on the bottom. And in the 1/2, I have a 2 on the bottom. So the 2 on the bottom cancels with the 14 and leaves a 7. We need to do negative 15 times 7, which is negative 105. And our units are feet per second. To determine the area of the curve from t equals 0 to t equals 16 is just adding the two numbers together in the previous two problems. 0 to 6, we had 60 feet per second, and from 6 to 16, we had negative 105 feet per second. So we just need to add those together, which gives us negative 45 feet per second. And finally, what's the area of the curve from 0 to 18? Now we know what it is from t equals 0 to t equals 16. We just figured that out in number 18. So we're going to take negative 45 feet per second and add that to our final calculation. From t equals 16 to t equals 18 is a right triangle. The base of the right triangle is 2, and the height of the right triangle is 15. So we're set up 1/2 base times height. 1/2, the base is 2 seconds, and the height is 15 feet per second squared. Let's cancel the units that we can cancel. The 2 will cancel with the 2 as well. So I will have to add negative 45 plus 15, which is negative 30 feet per second. Okay, so now you've learned that area under the curve can represent something in real life, and we have a way to represent negative area. When the curve dips below the x-axis, then you would consider that negative area. In the situation that will apply this in calculus, we'll talk about the positive area taking us in a positive direction, and then when we have negative area, that just means the person has turned around and come back toward in the opposite direction, so we consider that the negative direction. It helps represent an event in real life. Go ahead to the closure problem and try this on your own. So you're going to turn off the video, work on this closure problem, and then turn the video back on to check your answer. The answer to the closure problem, we're only concerned with going from x equals negative 2 to x equals 10. So negative 2 is here and positive 10 is here. From negative 2 to positive 2, we have a triangle. And then from positive 2 to positive 6, we have a triangle. And then there's another triangle from 6 to 10. So we're going to use 1/2 base times height to calculate area. 1/2, the base of the first triangle goes from negative 2 to 2. So the base is 4. And the height is 4. Notice we don't have to look at units in this closure. We're just figuring out the area. Then the second triangle goes from x equals 2 to x equals 6. So that's a base of 4. So I'm going to also set up 1/2 4 times a height of 4. But then when I go to add on the last triangle, the base is 4 because it goes from 6 to 10. But the height goes down below the x-axis. So the height is going to be written as negative 4. So 1/2 base of 4, height of negative 4. That way I remember to treat it as negative area. And that gives me 8 plus 8 minus 8, which is positive 8.